All right, we're going to start looking at gases, but gases are kind of hard to study in chemistry at first in the lab because most of them are invisible, or if they are visible, they're very dangerous, and so we don't want to inhale them or get them anywhere close to our skin and things like that. So before we get into looking at the macroscopic properties of a gas, in other words, how the pressure and volume and temperature relate to the gas as we squish it or we release it into a larger space, we crank up the heat and things like that. For our level, for what we can see, for a bulk amount of gas, we should probably figure out how the pressure and volume and temperature relate to each other at a level of particles. How those particles move around and bounce into each other and bounce against the walls of the container mean a lot. So the way we're going to do that is use this simulation that's linked here, and it should also be linked on the Schoology. So either way, we're going to get to a simulation that looks something like this. Okay, we'll be greeted with screen something like this, where we've got a couple different options here, and we're going to go with this leftmost one, ideal. Something we'll kind of get into later. Gases in chemistry, in actuality, are a little complicated, but we simplify a lot of things about how we think about gases to make it a lot easier to deal with them. So when we say that a gas is ideal, it means ideally this would be how a gas would act, and we kind of ignore some of the weirder stuff where a gas would be um, you know, clinging to other particles or the inside of the container a little bit due to the attraction between particles, or we realize that the gas does take up some space for itself. It's not just the size of the container. Some volume is excluded and things like that. But this is a nice simulation because it cuts out a lot of that stuff and follows what we call the kinetic molecular theory. Essentially, how do we imagine gas particles moving around, and how do the properties of a gas all relate to what those particles are doing? So we're going to click on ideal. It's going to load up our simulation like this. Now, before we do anything, we've got an empty box here. Let's see if I can get rid of this. There we go. We've got an empty box here. This is going to be what we put our gas particles in. Well, this box, has no gas particles in it. It has no matter in it right now. So without any particles to be bouncing around and doing their thing, well, temperature is just a measure of the average kinetic energy of particles. If there's no particles, there's no temperature, which is why we have this dash here. Okay, it's like we can't really measure temperature of nothing. We got to have a temperature of something. Same goes for pressure. Pressure is a measure of force on an area. If we don't have particles bouncing around and hitting the inside of the containers, bam, 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 well, there's no pressure. So inside this box, we have what we call a vacuum, not like a, clean your floor kind of vacuum. This is like a void of space kind of vacuum where there's nothing, essentially. So no matter means no temperature and no pressure. So right now our temperature is reading as, well, it's not even really a zero. It's like kind of a dash of Kelvin. And then our pressure is 0.0 atmospheres. Okay, so on our lab, we have one of our first questions or two is about that initial temperature without gas particles. Well, you could say that your temperature is 0 Kelvin, or you could put a dash. That's also fine, just like it says in the simulation. Okay, and our initial pressure without particles is 0.0 atmospheres. And those are the two places we're going to be looking for most of our data in these simulation labs is what's the temperature like, what's the pressure like. There's one more place that we'll see here in a little bit. Okay, well, in order to figure out how the gas particles do stuff, we need gas particles. So let's go put some in. Okay, so I'm just going to put in 2 pumps for my bicycle pumps. There's 2. All right. That's quite a bit of particles. If I want to know how many particles are in my box, I just look over on the right side where it says particles plus right here. And I can open up this box. And then it tells me how many particles I have. Right now we're looking at these blue particles, which they call the heavy particles, which means they're a little bit bigger. All right, and right now I've got 100 of them. I could use these little arrows to add one or subtract one from the box, to remove one, okay? Or I can use these double arrows to do kind of like 50 at a time, or remove 50 at a time, something like that. Okay, in this first simulation, we're going to be looking at the relationship between the pressure and the volume of a gas. So I don't want temperature to get involved here. I don't want temperature to be changing and stuff while I'm doing things. Okay, so reset this, pump my gas particles in. They're going to bounce around. Okay, just to double checking, and I've got 100 particles. You don't have to have exactly 100. It could be 90, it could be 125 or 150. Doesn't really matter, as long as we watch the relationship between the pressure and the temperature. Sorry, pressure and the volume. Okay, so I'm going to hold temperature constant, so that way temperature is not kind of interfering with our results. It's not changing while we're trying to measure these other two things. So I'm going to hit this little bubble for temperature, so that way I've got my pressure that's going to be changing, and I can still change the size of my box, which I've got this little handle over here for. Okay, so volume is typically 3 dimensions, length times width times height. To make it simple, this is just width times height. Okay, width this way, height this way, and our height of the box is not going to change, just the width. Okay, just going this way across. Okay, but the idea is the same, whether we're talking about area or volume. The size of the container, okay, should have something to do with the pressure. Okay, so when I say volume, I kind of mean area in this case, but I'm going to keep calling it volume because that's how we're going to see it later. Okay, so the volume of our container, okay, has to do with how much space our particles have, and the pressure is about how the particles hit the inside of the container. You might notice on your pressure gauge that a pressure is not sticking around one number like it would be on an actual pressure gauge you see in real life. Okay, when we're dealing with a ton of particles, okay, we kind of have this noise of what all these little particles are doing, kind of levels out a little bit. It's kind of like there's so much going on that you don't hear all the individual voices, so to say. You don't feel all the individual little boom, 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 boom hits of each individual particle on the inside of the container. Okay, but in this tiny, tiny scale where we're looking at the scale of atoms, we can see that. We can feel that. We have all these little particles that are hitting the inside of the container at different times and at different speeds, which means they're delivering different amounts of force at different times, which means a different pressure. So our pressure is not going to exactly stick around at one specific value. It's going to kind of float, and it's going to kind of bounce between a couple numbers. So whenever we record the pressure, we're just going to kind of pick something in the middle of what's floating between. So right now, and it looks like it goes up to about 12.1. It drops to about 11.3. So you can just kind of pick something in between there. So maybe like 11.6 or 7, something like that would be fine. Okay, so let's see what our lab is requiring us to do next. Okay, we put gas particles in the box. Okay, and we are holding temperature constant, which is good. Okay, we've got a couple questions about how the pressure changed. Okay, if you ever need to go back and try something again, there's this little orange reset button down here. So if you're like, ooh, I didn't watch the pressure I was putting in particles, well, you can just hit this reset button and then start over and see how it goes. Usually it's pretty fast to get back to where you're at. Okay, what are the particles doing to the inside of the container to cause pressure? Well, pressure is just force on an area. So if those particles are bouncing around, they're going to be boom, 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 hitting the inside of the container. That's force that they're exerting, okay, that they're pushing. Okay, so the particles are hitting the inside of the container to cause that pressure. Now, finally, if we want to figure out the relationship between pressure and volume, we need to change the size of the box, and we need to know what the size of the box is when we change it. So in our simulation on the right side, we have a little option for seeing the width of the box. Okay, and we're going to pull the handle to change the width to be specific sizes. Okay, you got another question about what you notice that's different as the area of the box gets bigger or smaller, and also what doesn't change. Okay, so you can kind of think about that and watch that when you do this in the simulation. What's different and what's not different. Okay, So we're going to be changing the width of the box and seeing how the pressure changes with this. To fill in this table down here, okay, this data table looks something like this. Okay, we're going to have a number of particles that we're keeping constant, so that way that's not interfering. Okay, if we have more particles to hit the inside of the container, more particles means more pressure. So we don't want to start changing up how many particles there are in the middle if we're trying to measure pressure in the process. Okay, the height of the box is also going to stay constant. Okay, it's going to be about 10 nanometers. Okay, this N is just a prefix, kind of like milli or centi. Okay, it's just for something very, very, very small. Okay, so nano is just another prefix. Okay, and then we're going to be changing the width of the box to be about these sizes. Okay, so this is the change we're going to be making. We're going to change what the width of the box is, and we're going to see what the pressure is going to become as a result of that. Okay, now we've also got this section over here to see the area of the box, basically how big it is, okay, other than just looking at the width. So if we take our height times our width, that is going to be our area, just like how 10 nanometers times 10 nanometers is going to be 100 square nanometers. Okay, so this is just going to be a quick multiplication problem to see what the area of your box is, and hopefully that will help you with some of the questions down below. Okay, so that you can do kind of at any time. Okay, what we need from the simulation is the number of particles that we have and the pressure that we have when we make the box this size. Okay, so let's go back to the simulation. I've got my particles in here. Again, I'm going to check off this box on the right side for width. Check that off. Okay, and right now my box is 10 nanometers wide, okay, which I believe is one of the measurements that we need. Okay, right now my pressure is kind of floating around, still the same sort of thing, 11.3 to like 12.1. So I would say my pressure is about like 11.6. That sounds fair. 11.6 or 11.7, something like that. So on my lab here, I'm going to write in my pressure for 10 nanometers. Pressure is about 11.7. And this is in atmospheres. Okay. How many particles do I have? I think I have 100 last time I checked. And again, we don't want to change that number as we go through this. Okay. Then I'm going to be checking these other widths to see what the size of my box is going to do to the pressure. So maybe I can make my box 15 nanometers. So let's go back to the simulation. Yes, I do have 100 particles. Ooh. On here. Oh, that's odd. My particles have started to kind of vanish. So I guess I'm going to reset this real fast. Boom, boom. I don't know why they're flickering like that. Let's reset the page. This will go to show how easy it is to set this back up. Ideal. Pumping my particles. Boom, boom. Ooh, they're still doing some weird stuff there. Okay. Well, it looks like it's still measuring my pressure. Okay, so aside from my particles doing some wonky stuff right now, check off the width. All right, and I'm going to make the size of my box 15 nanometers. Yeah, well, they're just having a party in there. My pressure is now down to like 7 to 8 atmospheres. It's kind of floating around 7.6 or so, 7.7 maybe. Okay, so I could go back to my lab here, and at 15 nanometers, we're sitting at about like 7. I'll do like 7.8. 7.7. We'll do 7.7. 7.7 atmospheres. Okay, so by doing this, you should find a trend, a relationship, okay, between pressure and the size of the box. Okay, these should be connected. Right? And the rest of the questions are basically about that. If we change the size of the box, what does that do to the pressure inside the box? Okay. Other particles in the box might start to change the pressure, so you can kind of check that too. We're going to pump some more particles in. Okay. And then also keep pumping particles in to see if something else changes. See what happens to the container when we got too many particles in there and what property causes that thing to happen. I don't want to spoil the surprise, so I'll leave that to you. Okay, and if our gas particles can escape from the container, what would that mean about the pressure? Okay, would the pressure increase, decrease, or stay the same? Last couple questions are sort of conclusion questions to wrap up what you figured out about the simulation, to think in our world standards. You know, what would happen in the real world as we use the ideas from the simulation. Okay, so hopefully the data that you get here will help you with that, to kind of figure out the questions down here for the rest of the lab.